Okay, welcome back to Calculus. Today we're going to be taking a look at section 7.2, and what we're going to start looking at is a new geometric measure, volume. We spent the last couple of days talking about areas between curves, and now we're going to start talking about volume. So three-dimensional measure, measure of an enclosed three-dimensional space, and we're going to use a method for calculating volumes called slicing. All right, so that's going to be the idea that we're going to be using for all of our problems. So as an example, if I were to draw you this cylinder, pretend that's a cylinder, and I wanted to calculate the volume of that cylinder, if I were not to have a formula, what we could do is we could start to slice this. And if I slice this cylinder in this direction, so pretend to put it on some sort of bandsaw or table saw and start making cuts across this, what we're going to find is that all of the slices are familiar to us. If I take one of those slices out, that slice that we're going to take out of our cylinder picture is going to be another cylinder itself. And so what we're going to do is we're going to think about finding the volume of one of these little cylinders. So we're going to find the volume of a little short cylinder, and the volume of any cylinder is going to be the area of the top, so pi times radius squared, where r is the radius of the circular top, multiplied by how tall it is. We traditionally call that the height. And what we're going to do to calculate the volume of the complete cylinder is we're just going to add the volume of that slice to 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 the volume of that slice. What we're going to do is slice the cylinder into an infinite number of slices, or really short cylinders. Okay? And it doesn't just have to be a cylinder. We could do the same thing with a cone. We could make cuts on the cone this way. Slice this cone into an infinite number of slices. Again, we're going to be finding the volume of every one of those individual slices and adding them up. How do we add up an infinite number of things? We integrate. So we're going to be integrating an infinite number of slices. And it doesn't matter really whether we have a cylinder, like we in that first diagram, a cone as in the second, or some crazy looking shape that I've got here in the third example. It doesn't matter. If we make slices, slicing this weird looking maybe vase into an infinite number of slices, again, all we're going to focus on is adding up an infinite number of these slices. These little short cylinders, we're going to add up an infinite number, and that's going to then become the volume of our three-dimensional shape. Okay, so we use the same process that Zoops would use to slice up one of those bad boys. All right, if you guys were a family that enjoys a ham, maybe with Easter coming up, maybe you guys would get a nice ham for supper. And if you put it on the slicer at Zoops and we made cuts through the ham, oops, sorry, forgot to hit my pencil there. If we made slices through the ham, all right, all of the slices are going to be familiar. We take any one of these slices out and lay it on our plate, all right? They are all going to look familiar. They're all going to have the same general shape. Of course, as we make cuts further and further to the left, the slices would get smaller. So a slice way back here somewhere is going to be a much smaller piece, but the idea is going to be the same. So we'll find the volume of all of these, add them up, and we get the volume of the shape that we started with. Okay, so we're going to find volumes in this fashion using two methods. The first is called disks. Disks essentially are just the name we give in calculus to really short cylinder. Whoops, sorry, spelled that wrong. Try that again. To really short cylinders. All right, really short cylinders are going to be called disks. And the process we're going to use is this one. We're going to create a planar region. Then we're going to rotate that planar region about a line. Then we're going to slice it into disks, these short little cylinders, and then we're going to add them up. Okay? And so just in general, not a specific example, but just kind of a general feel for this, we start with a planar region. So we're going to start in a two-dimensional XY coordinate system, and we're going to create some two-dimensional shape. We'll just keep this one nice and easy. Just some sort of curve that opens up nice and easy to the right. And then if I use a vertical line and a horizontal line, I create a two-dimensional planar region. So this is, right now, a two-dimensional, I was going to add that to the definition, 2D planar region. Planar just means in a plane. Okay? Then what we're going to do is we're going to take that two-dimensional planar region and rotate it about a line. Now we're going to have the majority of our problems either make the rotation around the x-axis or the y-axis. As an example, if we were to do it around the x-axis, we're going to take that shape and rotate it around the x-axis. What's going to happen is we're going to end up with kind of a mirror image down below, but then we have to pretend that this is getting spun around 360 degrees. All right? And when we spin it around 360 degrees, then the shape that we get is this now three-dimensional shape. Now I'm going to make the end look more circular, and I'm going to give it a little bit of a waistline, all right, pretending to kind of put a little belt on this thing to get it to look three-dimensional. So we're going to start with a two-dimensional region, rotate it about one of the axes normally. We can rotate it other places, but normally it'll be the x-axis or y-axis. And then we create this three-dimensional, so this is meant to look three-dimensional. Okay? And then once we have the three-dimensional object, we're going to slice it into discs. Okay? So in this case, we're going to make slices this way so that they all look familiar. They all look to be circles or short cylinders, discs. Okay? And then finally, to add up all of the individual cylinder volumes, what we're going to do to calculate the volume of the original shape is we're going to add up an infinite number of cylinders. Cylinders are pi times r squared times h. Okay? Just as we discussed before. But in calculus, we don't use the sigma any longer. When we want to add up an infinite number of things, what we're going to do is integrate. All right? And so we're going to integrate pi times the radius squared. And now one little thing I want you to keep in mind as we move forward, when we start to create integrals, the height of the cylinders is going to become our differential. All right? So it's either going to be a dx or a dy. And I'll explain how you can figure out which one is which as we move along. Okay? So that's the basic idea in how we're going to calculate a volume using the method of discs. Okay? So let's run through an example to see how it can be applied to a specific problem. So here's a specific problem. I'm going to start you guys off with the function y equals x squared. All right? I'm going to also ask you to use the line y equals 3. And I'm going to ask you to rotate about the y-axis. So how do you get a problem like this started? You begin with a picture. You start by drawing a two-dimensional planar region. So we start by drawing the two equations, y equals x squared and y equals 3. Y equals x squared is just our basic parabola that opens up from the origin. That's one you guys should know well. And y equals 3 is just a horizontal line through 3. Okay? So what two-dimensional region did we create? This one right here that I'm trying to shade in black. Okay? Now what we're supposed to do is take that two-dimensional planar region and rotate it about the y-axis. The y-axis being the vertical one. So we're going to rotate it. Let me put that in red so it stands out a little better. We're going to rotate that about the y-axis. And if I try to draw that so that it looks kind of three-dimensional, the three-dimensional shape then would look something like that. Again, trying to put a little belt line or a waistline or a equator on that thing. That would then be the three-dimensional object. Okay? So again, just to review, start by drawing the planar region. Next, rotate it about the line. We rotate it about the y-axis. Step 3, slice it. Slice it. Now, we don't want to slice it this way. You might think, well, gee whiz, I've got a choice. I could slice it however I want. But if we were to slice it this way, I'll erase this in just a second. But if we were to slice it this way, the shape that we would get when I lay that down is flat on the top and then a curve below. And you guys don't recognize that shape. You don't recognize it as something you could find the volume of. So we're not going to slice that way. Instead, we're going to slice this way. So we're going to slice horizontally so that every one of our shapes turns out to be a short little cylinder. And again, the idea is a short little cylinder, the volume is going to be pi times r squared times h. Okay? So then we're just going to not only take the volume of that slice, but the one on top and the one below and the one on top and the one below and the one on top and the one below. And what we're going to do is add up all of those. So to calculate the volume of the three-dimensional shape then, we're going to integrate. And now what we've got to consider, guys, is where is the bottommost slice going to be located on our picture, and where's the uppermost slice going to be located on our picture. Okay? Also, we're going to have to consider the radius of this short cylinder disc, and we also have to consider the height. Now, if you'll trust me for 1 second, what a really good place to start is to consider the h. Remembering the r stands for the radius of one of our discs, and h stands for the height. My question to you guys is this really, really short height vertical or horizontal? Is it an up and down measure or a side to side measure? And I hope you can tell from the picture right here. Let me select my laser pointer. So right here, here's the height. Please notice that the height is vertical. The height is up and down. And if it's up and down, that means our differential is going to become dy because it's vertical. So this height has to then become dy. Well, if the differential is in terms of y, then the limits of integration have to be in terms of y, and r, the radius, has to be in terms of y. So can we accomplish all of that? Sure. The limits of integration, again, are going to be the places where our very bottommost disk is located. And where is that going to be? 0. And the upper limit of integration is going to be where the topmost disk is going to be, and that's going to be located at 3. So for our problem, we're going to be integrating from 0 to 3. And then what are we integrating? We're going to be integrating a pi, and we're going to be integrating an r squared. All right? Now, again, just one more time, because the limit of integration are in terms of y, 0 on the y-axis to 3 on the y-axis, and the differential is in terms of y, the radius also has to be in terms of y. Okay? So how do we accomplish that? How do we get the radius in terms of y? Well, what I'd ask you to notice is that the radius for our single disk over here, for our single disk, please notice that the radius is side to side, horizontal. And if something is horizontal, how do we want it to read? We want that to read then as x equals, right? If it's side to side, if it's left and right, that has to read as x equals. Well, unfortunately, the equation for the parabola isn't in terms of x equals. Right now, it's in terms of y equals. It's actually equal to y equals x squared. But can you guys help me switch that so it reads as x equals? Well, heck yeah. All you have to do is get rid of a power of 2 by taking the square root. So if we take the square root of both sides, we'll get x is equal to, usually would say plus or minus y. We're going to disregard the plus or minus right now because we're just going to be talking about a distance. And so the radius then is going to be the square root of y. All right? And hopefully it makes sense when we go back to the picture. If I use red and give you the radius, this side-to-side measure, for any one of the discs, show you that side-to-side measure. It's always side-to-side, so it has to read as x equals. All right? And so what we've ended up with at the end is an integral where the lower limit of integration is in terms of y from the y-axis. The upper limit of integration is from the y-axis. The radius is in terms of the radius is in terms of y, sorry about that. And the differential is in terms of y. All of those always have to match up. You can't have x's in one spot, y's in another spot. Now, is that something you guys can integrate? Yes. What I would ask you to do is factor the pi out front of the integral and then square what's inside. So the square root of y squared is y. And let me move the screen up a little bit so we can now show the rest of the work. Do you guys know how to integrate y? Well, of course you do. Add 1, divide by the new. So power rule, add 1 to the power, divide by the new. And then we're going to be f-ticking from 3 down to 0. So I'm just going to leave the pi out front and then do the f-tick. So put in 3, so 3 squared over 2, minus, put in 0, 0 squared over 2. And what we'll end up with then, guys, is 9 halves pi. And so the volume of our solid formed by starting with the two-dimensional planar region and rotating it around the y-axis would be 9 pi over 2. Now, most of the problems I do in class, I'm going to leave things as exact values. I'm going to leave it in terms of pi. But if you guys would prefer to punch this out as a decimal, absolutely feel free, all right? It's just totally up to you. Okay, so if I shrink that up to try and get it on one page, there is a good example of one problem where we're finding the volume by rotating around the y-axis. Okay, let's do another problem, but this time rotate around the x-axis. So here's another example. Let's go with y equals e to the x. Let's use x equals 0. Let's use x equals 1. And let's rotate about the x axis. And I'm going to ask you to find the volume. I'm going to ask you to find the volume of that solid. So where do we get ourselves started? Drawing a two-dimensional picture. So we start by drawing y equals e to the x, and if you don't remember a basic exponential, don't worry about it, use your calculator. So y equals e to the x is just our basic exponential curve function. Then x equals 0 is just a vertical line through 0. It's kind of hard to draw because the y-axis is already in the way. And then x equals 1 is a vertical line through 1. Okay? And so the two-dimensional region that we're talking about then is this one right here. Okay? So start by drawing the two-dimensional planar region. Then, second, rotate around the x-axis. So of course the x-axis is the horizontal. So now we're going to rotate that two-dimensional region around the x-axis. And what I like to try and do is I like to try and get a mirror image on the other side of the axis. So I'm just going to draw this kind of mirror image down below the x-axis. And then when I rotate it, I'm going to try to get a shape that looks something like this. I'm going to do the best I can. All right? All right, so that's the basic three-dimensional shape with the x-axis going through the middle of it. That's where the rotation was being made. Okay? Now what we're going to do, step 3, is slice this fella. Now we're not going to slice it this way because, again, the shapes would be unfamiliar to us. What we're going to do instead is we're going to slice it this way, because when I slice it vertically, every one of the shapes becomes a disc. All right? And we know how to calculate the volume of a disc. It's going to be pi times the radius squared times the height. Okay? And then to calculate the exact volume of the entire three-dimensional shape, we're going to integrate. And again, I'm going to start you guys off with the differential All right, what kind of differential are we going to have this time? Well, because the differential is always going to be the infinitely skinny height, if I put this in red, please notice right below the H here, the infinitely skinny height is side to side, left and right, side to side. And if it's side to side, that means the differential then is going to be dx. So the H is going to become the differential dx. Okay? Now, because that's in terms of x, everything else has to be in terms of x. The limits of integration have to be in terms of x. Both the lower and upper have to be in terms of x. Then we'll have a pi. And then our radius also has to be in terms of x. Okay? So let's see if we can figure out all of those. Where are the limits of integration going to come from? Well, they have to come off the x-axis. So where is this very first disk going to be located when I transfer it back here? The first disk is going to be located at 0. And where's this last disk, this biggest one off to the right? Where's that last disk going to be located? Well, that backs up to being at x equals 1. And then what I'm going to be integrating is, whoops, that's a terrible pi. We'll try that again. So we're going to be integrating pi times the radius squared. So the last thing we have to do then is we have to fill in the value for r. Okay, but when you look at your picture now, let me go back to my laser pointer. There's r in our slice. And in what direction is r? R is a vertical measure. And a vertical measure needs to read as what then? A vertical measure needs to read as y equals. And is that what I have? Looking back to the first equation? Yes. So therefore I can replace r with e to the x. Okay? So I've got my limits of integration, pi, r, which is now going to be e to the x, squared, and h is the differential dx. Okay? So we create the definite integral from 0 to 1 of pi times e to the x squared dx. And what I'd expect you guys to do then is be able to evaluate that definite integral. Okay? So please factor out the pi just to get it out of your hair. Remove the parentheses. E to the x squared is e to the 2x. Then integrate and f-tick. Unfortunately, this one requires a u substitution because we don't have a rule for the integral of e to the 2x. So we'd have to do a u substitution. Replace 2x with u. But anytime I ever make a u substitution, I have to take the derivative of the substitution. So 1 du is going to be equal to 2 dx. There's no extra 2 laying around, so I've got to divide that to the other side of the du dx equation. And now I can make my substitution. Okay? I still have the pi out front. Instead of e to the 2x, I'm going to have e to the u. Instead of the dx, I'm going to replace dx with what it's equal to, which is 1/2 du. But please notice I just put the half out in front of the integral. And then a couple of days before school was called off, we went over something called a change of variable. And the idea was that anytime you guys are doing a definite integral that required a u substitution, you had the choice to doing what's called a change of variable. And if you would want to do that here, I told you at the time that for the rest of the year I was going to be asking you guys whether you wanted to do that. I'm just going to choose to do it. I'll use some arrows though to help you remember. Whenever we make a u substitution, we can actually replace the numbers in the substitution with, in this case, 0. So if I replace x with 0, 2 times 0 gives us 0. And if I replace x with 1, 2 times 1 is 2. That's called a change of variable. And what that allows me to do then is f-tick without switching back to x's. So because I did a change of variable, I don't need to change u in the exponent back to 2x. I can just leave it as u because we changed the limits of integration to being in terms of u's. And now I can f-tick, replace u with 2, and then replace u with 0. Again, just leaving the pi over 2 out front. And so my exact answer would be pi over 2 times u squared minus 1 cubic units. I know some of you might not like it this time. So I'm going to approximate that for everybody, because I know some won't like that crazy looking expression. So I'm just punching it out on my calculator here. Just take me a second. And 2, so I punched OK, I believe, and I got approximately 10.04 cubic units. And again, for the rest of the year, either exact or approximate are totally fine. Totally up to you. Okay? So I'm going to pause this video so that you guys could have a break. And then I think I'm going to move on to the second method of finding volumes. And then I might include a third video in this section just going over some examples, some further examples of volumes by discs, and then the second method that's going to be called washers. All right? So you should be watching this on Thursday, I think, if you're following the schedule. So we'll see you again tomorrow then.